see me?
Oh my
Yeah.
God.
Wow.
With you probably laying in the woods somewhere, probably not. Huh? Yeah, 15 minutes left out.
So in honor of Halloween, if you would like to come down and get one or two candies off the front desk, then you are more than welcome to. Happy Halloween.
Thank you.
You're welcome. You're welcome. So let's see, this is actually All Hallows Eve, right? Or is that tomorrow night? And then Sunday would be Dia de Muerte, right? The Day of the Dead. It's in celebration of all the ghosts that live in our house, right? Yeah, South America.
It's supposed to be a full moon this weekend too.
Yeah, so all the werewolves will be out.
Happy Halloween.
Yeah. You guys are coming in, if you would like a couple pieces of candy, chocolate, whatever that may be, you're more than welcome to come down and get a couple. You're welcome. What do you guys think? I almost went cowboy, but this was just kind of too tempting, right? I'm not sure I can lecture in it, I'm gonna be really honest with you. Inside of this, it's about 25 degrees warmer than it is the room. This would have worked really good on Tuesday, right? But today they have the heat on and it's kind of a little unpleasant, right? But was it fun to come in and, yeah, I didn't know if you guys could see me or not. You know,
Well, what is on the heat on the warmest day of the week?
yeah, I mean, that's normal for a year. So anyway. If you would like a piece of chocolate or candy, you're more than welcome to come by and everybody your seat and grab that. And I'm going to give out this. That's all right. We'll save it for the next hour, right?
Oh no, you magically appeared.
I magically appeared. Oh, that's much better tip, so I just get that off. Whew. So I think there's supposed to be trunk or treats on campus. You get to dress up and, you know, have fun a little bit. It's going to be a interesting Halloween. We've hosted a Halloween party at our house for about 20 years. And so this will be the first year that we are not doing that since we've lived in Branson. Chili and hot dogs, right? Build a bonfire in the backyard for the kids, and you know, but, you know, my kids are growing and not as interested in it anymore, right? So, so we actually were doing a math problem last time, and it was heat transfer, right? And so we had two objects. Actually, do I have any housekeeping? I couldn't think of any. I don't think so. Right? So, yeah, go on, roll. All right, here we go. Heat transfer. Heat moving from one object to another. Do I only have a red marker? That's not good. Well, I guess we'll try it in red. Can everybody see red? Yeah. Oh, there's one. Wow. Good call. So we were actually looking at the Q of iron, right, equals negative Q of the water. I believe that's the way we set that up, isn't it? Yeah. And so then we were defining those terms, and we had substituted for this what? MC delta T for the iron. And then the same substitution over here for the water, right? And so then we actually started plugging in the numbers to solve the algebraic expression. And what did we plug in for the mass of iron? 100 grams Fe. And what did we plug in for C? 0.106. And the units on that are calories per gram per degree C. All right, and then we did T final minus T initial, and what was the initial temperature of the iron? 100 degrees C. And then that was equal to the mass of the water. What was the mass of the water? 200 grams, right? And in calories, what is the specific heat of water? 1, right? So, oops. So 1 calorie per gram per degree C, and should put multiplication sign in there.
And you said if we were like having a test, you would tell us this.
Yes, I'd give you the specific heats, yeah, no doubt. And so then, what was the T final, or we don't know the T final of the water, right? But the T final of the water is going to equal the T final of the iron, right? Because they're going to come to equilibrium. Cool, you guys with me? So that's the X that we're solving for. What was the initial temperature of the water? 100 degrees Celsius, or 20 degrees Celsius. I'm going to put that on the outside to make that more straightforward. So I basically just factored out degree C on both the temperature equations. Is that okay? And then that way they can distribute when we need it to. All right. Now, all I have to do at this point, I have it set up. What am I going to do? How do I finish this? I solve for TF, literally. And so, in my mind, I would probably start by multiplying these two together, right? And then I would multiply those times the two temperatures, okay? The response to that, right? So what's 100 times 0.106?
10.6.
10.6.
What was the?
All right, and our grams are going to cancel out of that, right, when we do that. And I'm going to be left with calories per degree C, okay? And then that's going to be times temperature final minus 100 degrees C. And that's going to equal, what's 200 times 1? Yes, I'm actually... All right, so now if I...
Was there a negative there?
Oh yeah, I forgot the negative, my bad. We'll still leave that in parentheses, we'll get rid of that at the end. Okay, thank you very much for noting that. I see I dropped a sign. See how easy it is to drop a sign? Now, sign, everywhere, sign, that's what comes to my mind. Messed up brain, but. All right, so now I would multiply these out, and so 10.6 well, that's interesting. My units aren't working out right. Guess I would stay on that when it multiplies back out. What's 10.6 times 100? Interesting. We have the answer to that up there, don't we? 10,060, is that right? Oh, I forgot something there.
It's 1,060.
1,060? That's what I wrote.
Is your degree Celsius would cancel there, right?
Yeah. But there's still degrees Celsius on the T final. So what's gonna happen is the calories are gonna cancel on the last step, and there's
Okay.
still degrees C on the TF. 20 times 200, 4,000. Am I right so far? All right, so go ahead and put the negative sign through over here is probably what I would do next. I did that by smearing away the parenthesis. And now I rearrange to get like terms.
You need to change the positive sign.
Right here,
Yeah, you're distributing the.
it was negative before, and so I multiplied through by -1, so it made it positive, right? Is that correct?
Yeah.
Yeah. And then this, there's a negative sign right here that goes on that 200. Right, so I think I got that right. Let's mark it done. So, where am I going? What's next? Combine like terms. So, we have, equals 10.6. Plus 200.
Yeah.
Equals 1,060 plus 4,000. And the units on these would be calories times degrees C, and these would be calories. Okay. All right, you guys can finish that, right? Because I just ran out of room on the board. And so if we did all of our math correctly, a moment of reveal, 24 degrees C. So,
Hang on,
yeah,
could you, so you add them and then you divide. Okay.
so we are in the same place on the board. So here's where we're at on the board, right? And when we divide that out, then the T final becomes 24 degrees C. Cool? You guys got that? Yep.
Is the specific heat of water exactly 1?
That's the defined number for that, yes.
So we don't have to worry about significant digits in that.
For that number, no, because it's a conversion, yeah. So, Cool? Questions, comments? More math, right? We're gonna use the same Q equation in about 3 different ways. So by the time that you get done with this, hopefully it will just come automatically. Realistically, you just need to define terms. You need to know what the mass is, or you can actually determine the mass, right? If you know the heat and the specific heat and the temperature change. But if you know those terms and can identify what to fill in and then what to actually look for, then these become fairly straightforward. I usually enjoy them. I won't say it's my favorite part of chemistry, but it's definitely not bad. Does that make sense? Should I say things like that? I don't know. Just quiet. Already got the sugar lull.
I've had this sugar roll for about 2 weeks.
I haven't ate one yet. I've been resisting. All right, the next problem. All right, this is a heating curve, okay? And so when I'm looking at this sample starts at negative 50 degrees, okay? And so then I start transferring in energy, okay? And when I start transferring in energy, then what happens to the temperature? It increases, doesn't it? And so while it's a solid, it increases from negative 50 to 0 degrees. Now, I'm going to ask a question. What do you think the identity of the material is? It starts melting at 0 degrees C. It's water, right? So freezing and melting. So ice forms from 0 to 50 degrees, from negative 50 degrees to 0, and we have to put in energy to do that. Now, what I want you to notice is that there is then a plateau, okay? And what is going on? We're still adding heat. We are still adding heat, but the temperature's not changing. Why?
Is it because it's still melting?
It's still melting. So the heat is all going to melting the solid to liquid. Right, you guys with me? And then once all of the solid melts, then what happens? The temperature starts to go up again. Okay, so you guys can follow that pattern. And in fact, for this particular problem, right, I have a tendency to just use numbers, Q1, Q2, Q3, Q4, but I'm going to define it right now. If I'm looking at those steps, I would have Q ice, right? So there would be a Q equation for that because the specific heat of the ice is different than that of liquid water. You guys with me? So then I would have Q melting, right? All right? Or I'm going to use a different word there, a better one. Let's say fusion, okay? Because that's the phase change from solid to liquid. And so if I add the heat that I put in for the heating from negative 50 to 0, and then the heat to melt, what's my third Q? Liquid. It is. So there's a heat to take the temperature of the liquid from there to positive 50 degrees, right? And so then that would be Q of liquid, or we'll just say liquid. All right. Now, the way I normally define this is I just go Q1, Q2, Q3, because I can do any process any direction that way, and it just helps me to organize my thoughts. Does that make sense? Yeah. And so anyway, now what these are equal to is the total heat for that process, a multi-step process. Cool? You guys with me? So we're going to do this calculation, all right, for water and from different places of starting and different places of ending. Okay? So this case is actually talking about a specific amount of water, and so if I'm looking up here, then it's to melt 1 gram of ice at 0 degrees C, this has to, well, in fact, what's the amount of heat that I have to put in to melt ice in joules? It's 1 calorie to melt 1 gram, right? Or is it? Wait a minute, is that the same number? Hang on. We need that number. Hang on, let's go down and look just a second. So I've got those right here, okay? So the QIs, I need 2 joules to melt ice, right? Now, to raise the temperature of water, then liquid water, I need 4.184, okay? I said that, gosh, I got the wrong one. To melt the ice is down here, 333. That's the heat of fusion, okay? Now, I want you to notice something. You see how those 3 have temperatures on them? And these 2 don't? Why not?
There's no temperature change.
Because there's no temperature change going on during that process. It's the flat line on the curve. So we have no temperature change, so it's not included as part of the equation, okay? So anyway, so we're about to set this up. Let's go back a couple slides. I just wanted to show you that where we were at when we were talking about the amount of heat that needs to be transferred, right? And so 333 joules per gram. And so anyway, to get that done. And then so anyway, this one we know is 4.184 joules per gram per degree C. And this one is 2.02, well, I'll say 2 joules per gram per degree C, okay? So, yeah, and do I want you to memorize those? No, because I don't have them memorized, right? I just look them up when I need them. By the time we're done with this lesson and I do it twice, then I'll have them memorized for this year, right? You guys with me? Mm-hmm. So anyway, heat. This is 1 gram of iron, okay? This is 1 gram of iron at 0 degrees C. So red hot, 738 degrees C, 0 degrees C, right? To this is 1 gram of liquid water to 1 gram of ice water. Now, there's no temperature change that's occurring there, right? In this, there's a temperature change, 738 to 0. So that's the same amount of energy in terms of quantity. Isn't that kind of crazy? Yeah. Or if we move over here to take half a gram of liquid water from 80 degrees C to ice, right? Half a gram, that's all of those are 333 joules. Okay, all of those processes. Why does the water not change as much as the iron does? You already know the answer to this. We talked about it last time. This is a concept question. Why does the water not change as much in temperature as does the iron? The specific heat of iron is much smaller than that of water. You guys with me? Yeah, so there's something to remember. All right, so just an idea. So phase changing, right? A system consisting of water at atmospheric pressure, and when we heat it, what's happening? What happens when we heat it? We put heat into the system, and the system gains energy. The water phase changes, right? And so the vapor puts pressure on the balloon and inflates it, right? You guys with me? And so then when we remove it from the hot plate and we set it on the cabinet and we let the heat dissipate, what happens? The balloon deflates, right? And so the amount of water in the atmosphere decreases because the water's condensing back out. And so, can we use this to do work? Is there such a thing as a steam engine? Yeah, where we use pressure to do work. And so I just want to point that out, that is part of this equation, right? And those changes in energy, even though what are we going to do with the work? Never mind. All right, you guys are way too quiet today. It's Friday. All right, you're supposed to be like chirping along and hanging out with me. So Calculating the amount of heat transfer and temperature and phase change, that's what we're gonna do next. And we're gonna determine what phases we're gonna go through. We're gonna find the specific heats for those phases. And then we're gonna build our equation and calculate the amount of heat that it's gonna take to go through that process. Okay, so that's what we're gonna do. And you could have as many as 5 steps for the normal phases, right? To go from solid to liquid to gas. Okay, you'll have 2 phase changes and then 3 regions of heating. So that would be the most complex problem that you could have. And so this would be one of those problems. How much heat is required to take 10 grams of ice from negative 15 degrees C to steam at 127 degrees C? Okay. What do you need right now? What are you looking for? You need to set up the Q equations, and to set those up, you have all the information except the list I gave you a second ago, right? Except for these. So here they are. So instead of being Q1 through Q3, what's it going to be? How many steps? Well, let's draw the curve. Maybe that will help. Okay? So when I was learning how to do this, I always found that this is not proportionally correct, so just bear with me on this, right? But this is 0, this is 100, okay? And we start at negative 15, right? You guys with me? And this is heat added, right? And then this is temp. And so I draw that. And in fact, it's in degrees C. And we're going to do that, the calculation in joules. Okay? So be aware of that. And so we start at negative 15 and we go up to 0, right? And then we phase change, and that runs parallel, right? Because the temperature's not changing. And then we heat the water, and this curve is actually a little flatter than this one. And till we get to where 100 degrees C, right? And then we phase change again, and then we continue on up. And what's the final temperature? 127. So 127. And that's our final place, okay? So beginning to end, so we're going to call this Q1, Q2, Q3, Q4, and Q5. You guys get that now, to make that connection? Right? And so if I take all of those and add them together, Q total is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5, and when I add all of those together, it gives me the total amount of heat that it takes to do this process. That's what the question is asking. Okay? So now all it becomes is what? Set up and crunch, right? So Q total equals MC delta T for Q1, right? So what's the mass? Well, actually, what's the mass for all of them? 10. So I can put in 10 grams, and then I need the ice specific heat. What's it? 2.06. And then what's the temperature change of the ice? What's the temperature final? 0, right? And what was temperature initial? T final minus T initial, right? What was the temperature initial? Negative 15, right? So putting that in there in that fashion. And so now I've got, that's Q1, right? guys do Q2? What is Q2? How many people wrote 10 plus 333? Or 10 plus, 10 times, excuse me. 10 times 333. What's missing then? The temperature changed, but what's the temperature doing in that step? It's staying the same. Okay, so, all right, so now I add the next one in, so we're gonna do Q3, and which specific heat do I need for Q3? The water one, so. And what's my temperature final for the water? And what was my starting place? 0. So now I've got Q3 done. I'll let you guys write Q4. Does this kind of get repetitive? So I wrote the last two terms up there, and so when we start multiplying this out, so there's my heating graph, right? The solid, the liquid, and the gas. The flat places are where the phase changes occur, fusion and vaporization. So those are what those lines are called, melting and boiling. If you look at the way this question, or fusion and boiling. All right, so. All right, so the answer is 31, right? $31,000. Joules or 31 kilojoules, yeah.
How much faster do you want it?
Very often, when these are that large a number, they're normally converted to kilojoules. Just to let you know that. We're going to start working with some standard values in your textbook. And what's interesting is the table gives one of the values in kilojoules, and actually two of the values in kilojoules and one in joules. And so whenever you do math problems with them, you have to do a conversion every time. It drives me nuts. Why not just put them all in kilojoules or all of them in joules? But the tendency is when they're large to make them kilojoules, when they're small to leave them in joules, depending on what they are. Cool? Yeah. What do you think? You guys do this? Yeah? I think you can. hope so anyway. So, I have a question, right? Oh, not this one yet, but this is another practice one. And what is the amount of energy that's required to take 50 grams of water from negative 12 to 0.5 to 107 degrees C? I'm gonna let you guys do this one on your own, okay? So your roadmap is right there, it's on the board, and see if you can solve this. This pretend like this is a quiz right now, and see if you have the ability to do this calculation. Okay? Would it be the same heating curve that we have on the board? Except we're starting at a different temperature and different mass? Yeah. So that's the only change in this calculation. Different temperature and different mass. Now, students sometimes ask me, can they calculate Q1 and then Q2 and then Q3, Q4 and Q5 and then find the answers for those and then add them together, and yeah, it's just doing it in a different algebraic order, right? Yeah. I have a question that sometimes is missed. If you're starting at negative 15 and you're plugging it into the T final and T initial equation, you need to keep the negative sign. And the answer is absolutely. Okay? steps take the most energy? Transitions take a lot of energy. In fact, the transition from liquid to gas is multiple times more than that from solid to liquid. You guys catch that? So that phase change from liquid to gas removes a lot of energy, and that's why they use towers, right, to remove heat from power plants and those types of things, which use water, and you'll notice that steam is leaving from those towers, right? It's not pollution, it's not from the combustion process. It's actually liquid water that is converted to gaseous water to do the cooling of the steam from the expansion to run the turbine. And so they need to get it back to liquid, and they want to use the same water in the turbine system because they pH adjusted it and make sure the mineral content is appropriate and all of those things, so that when it goes to steam, it doesn't damage the system, okay? And so they recycle that water, and to get it to expand enough to run the turbine, then they have to have it in the liquid state to start with, and then expand it into steam to get the pressures to run the velocities that they need to generate, okay? So that's just something to notice, right? And then to take it from from 0 degrees to 100 degrees takes a lot of energy too, right? To get that transition to happen. So heat is easily removed with water because of its high heat capacity. So anyway, this is a great question, right? This is for those people up there who, I'm dieting right now, okay? So if you've thought about losing weight, then people say you can eat celery because, you know, it's negative calories. I'm not sure that's true or not, but okay. They also say that you can chew on ice and to eat some ice daily to burn some extra calories. And so what I want you guys to do is, suppose you eat 100 grams of ice. So we're going to make it -2 degrees C, right? Because if we put too cold ice in there, we might freeze the cells in our mouths, and so we don't want to do that, right? We don't want to stick the ice cube to our tongue, right? Or the flagpole, like in that movie. What was the name of that movie? Christmas Story. Yeah, that's a good one. That's coming up, Christmas. So anyway, so we don't want that time. So we're going to have 2-degree ice, and we're going to take it up to body temperature, 37.5 degrees C. Now, I have a question. Is this going to have 5 steps in the calculation?
No, check 4.
No, is it going to have 4 or 3? 3. It's going to have the temperature rise from -2 to 0, the phase change, and then up to 37 degrees C. So this is a simpler problem. I made the last one easier than the first 2. Right? So I'm going to let you calculate this one again. Let's see. You're going to have to do some conversions, right? Well, you could actually do this with the specific heat in calories, right? If you had that. Or you can do it in joules and then convert to calories, because those are the specific heats that we have, right? Oops, don't want to give you that. Do it in joules, and there's those specific heats that you probably have them already. So, but from -2 degrees C, how much ice was it?
100 grams.
100 grams, okay? 100 grams. -2. Now is that a lot of ice?
Decent amount.
It's a decent amount of ice, yeah. So just set out a big cup, right? One gram per milliliter, right? so how many joules is this? 49 kilojoules. Or 494,000. Nope, 49,400. Tried to get an extra zero on there, didn't I? Joules. And I put it in joules because I know the conversion. It's easier for me to do joules to calorie. Now that sounds like a lot of energy, doesn't it? You guys with me? Does that sound like a lot of energy to you? It does to me. Okay? But let's do some more converting. Okay? And so to get that in from joules to experimental calories, what's the conversion?
4.18.
49,400 joules times 1 calorie over 4.184 joules, right? And then I need to do one more conversion. What's the next conversion? Because that up there has a what in front of the calories? Has a big C, doesn't it? And this is a little c. Okay? So how many little c's are in a big C? 1,000. So times 1 food calorie divided by 1,000 experimental calories. Everybody got that?
11.815.
11.815, we would make that, let's round that to 12 calories. What do you think? Is it a worthwhile endeavor to melt ice for weight gain or loss? No, doesn't do a lot. I mean, just throwing that out there. Cool? You guys with me? You know, kind of like eating celery is negative calories. All right. 11.8 calories. 11.8. It should be 2 sig figs, so it should be 12 because of that negative 2C right there, right? I'm not very good at sig figs now. All right. We'll stop there for today. Next time we'll pick up, and there's a second half of